Hello everyone, welcome to the course on microsensors and nanosensors. We are in the 8th module where we are discussing about tactile and pressure sensors. We already have discussed tactile sensor, and in the previous class we talked about pressure sensors. In the previous lecture we have learned about different sensing elements and different transduction techniques that can be used to detect pressure. Sensing element, we have seen that it is mostly based on diaphragm, plate or membrane, okay, and of course the transduction technique can be very wide, including piezoresistive, capacitive, piezoelectric and optical. So what we are going to do today is we are going to see that how a diaphragm or a plate can be used for pressure sensing. Of course, if you are using a diaphragm or a thin film or a thin plate, you should know the surface area where the pressure is being applied. Okay. So let us consider a membrane which is basically a thin diaphragm, and this membrane is under a radial tension S. Okay. So consider this plate which is hinged between two blocks, and there is a tension S, in this membrane, okay, and the radius of this membrane is r. Therefore, this diameter that I have covered is 2r, and due to this pressure it can bend to a maximum distance from its original position to Z max. Okay. So the tension that is measured in the unit of Newton per meter. Okay. So we will use this S in the derivation of some equation, okay, where this Z max and the applied pressure relationship will be established. Okay. So please note that the unit of the tension is Newton per meter, and accordingly you can understand that you are applying the force per meter. Okay. So that is the basically tension we are talking about in such a thin film or a diaphragm case. Okay. So bending stiffness can be neglected in this kind of membrane, because the thickness, say if the thickness of this membrane is, I am calling it as a G, okay, and the radius was r, so G by r is at least 200. Okay. So bending stiffness can be neglected since the membrane thickness is significantly smaller than its radius, and in this course we are considering that at least the ratio between the thickness G and the R should be 200, okay, or anything above 200. Okay. Of course, it should not be very high, otherwise it will be very difficult to membrane to sustain. Okay. It will immediately break on its own weight. Okay. So it should be balanced out, and usually for the case of membrane or a thin diaphragm, we are taking it at least to be 200. We will see what is its ratio when we consider a plate, that this should significantly change in that case. Okay. So when pressure is applied to one side of the membrane, in this case this side of the membrane, it deforms into a spherical shape. Okay. So when you apply a pressure to this membrane, this will keep on deforming till it can, okay, and it will actually take a shape of sphere, very similar to soap bubble. Okay. We have seen that how it take a shape of sphere when you apply a pressure. Okay. So at low pressure, differences across this membrane, the center deflection Z max, stress, say I am calling it sigma max, are quasi-linear function of pressure. Okay. And the exact mathematical equation between this Z max and the pressure is Z max is equal to R square into P by 4S, where S is the applied tension, okay, when it is hinged at 2 point. Okay. The maximum stress sigma is S by G. Okay. So what you can also do is for the condition when there is a maximum deflection in this plate, you can also calculate the maximum stress in terms of pressure. Okay. So, in this two equation, R is the membrane radius, Z is the thickness and S is the radial tension. Okay. What I can do is basically I can substitute this S in this equation in terms of Z max. So, if I see S will be equal to R square into applied pressure. Please note that this pressure that I am talking about is low pressure. Okay. Since we are discussing the course on microsensors, we are not talking about high pressures. Okay. So, this tension is in terms of this Z max can be written as R square P by 4 Z max, right. And if I substitute this in this equation, this sigma max will be R square into P by 4 Z max by G, right. So, what you can do is you can write this equation of maximum stress in terms of pressure. Okay. So, if you see this equation, this Z max is actually directly proportional to pressure. That is why I initially mentioned that it is a quasi-linear function of pressure. I am not telling linear because I have a constant that this pressure is a low pressure. If I keep on increasing the pressure, this equation will no longer be valid. Okay. Similarly, we can see that this stress is also a quasi-linear function of the applied pressure. Okay. Now, when the thickness of the membrane is not negligibly small, okay, what it means is the ratio G by R is now not very small. Okay. So, the ratio G by R is now say 100 or even smaller. Okay. In that case, the structure is no longer classified as a membrane. Okay. Since the thickness is not negligible in comparison to the radius, we will call it as thin plate. Okay. So, this is the two images. This belongs to a membrane and this one is a thin plate. Okay. So, this thin plate is hinged with the same structure that you have seen for the case of membrane. Okay. Please note that hinging this plate with these two blocks and applying pressure can cause significant amount of friction at these 2 points. All right. So, because of course, it has its own weight and it has its own thickness. Okay. So, basically when a plate is compressed between a clamping rings, these two clamping rings, there is a friction that develops between this thin plate and the clamping rings. So, when you apply pressure, there is a high chance that this will also have slight movement. Okay. And this is the basis of having hysteresis in this kind of device. Okay. So, hysteresis is the major challenge in this kind of pressure sensors. Okay. So, what people has done is to avoid this kind of hysteresis, they have come up with one piece structure. Okay. In that structure, this these three components are not different. They are extruded from the same metal or it is taken out or machined from a single piece of a bulk material, very similar to like say if I am making very sensitive plate based pressure sensor using say for example platinum. Okay. What I will do is I will take a block of platinum and I will machine out something like this kind of structure. Now, the sensor will look like when you apply a pressure say in this area, this is the known area, you are applying the pressure and this will bend, this will try to take a spherical shape, but there is no slipping and no hysteresis. Okay. However, of course, the device will not be that sensitive as compared to the previous one. Okay. So, if you see, the plate as well as the supporting components are machined from a single piece of a bulk platinum in this case. Okay. So, for this kind of structure, for a plate kind of structure, the maximum deflection is linearly related to pressure, and the Zmax is given as 3 into 1 minus Poisson's ratio square into r to the power 4 into p by 16 e into g cube, where this e is the Young's modulus. Okay. So, Young's modulus and material strength becomes very crucial in this kind of device. Okay, because that will decide if the Zmax, how much Zmax can be achieved using the structure. Okay. So, Zmax is given as 3 into 1 minus square of Poisson's ratio into r into 4 into p by 16 e g cube. For the thin diaphragm or membrane based, it was 4p square, Zmax was r square p by 4s, right. So, this Zmax and this Zmax, they all are dependent on the radius of the membrane as well as the plate, but their dependency is quite different as compared to each other. Here, for the plate, Zmax is proportional to r to the power 4, while its dependence in case of this membrane is not that high. It is Zmax is directly proportional to r square. Okay. Here, since it was clamped at 2 points, the tension was playing a very crucial role, while the material strength is something which is very crucial in case of plate based device. These are some small takeaway from the structure of a diaphragm based devices and a thin film based or a thin plate based device. Okay. And their applications are also quite different. Okay. So, there are applications where this diaphragm or a membrane based devices are more useful, while there are some applications where the thin plate based pressure sensors are more useful. Okay. Please note that the maximum stress at the circumferences is also a linear function of pressure in this case, where the sigma max is given as 3r square into p by 4g square. Okay. For the membrane based devices, sigma max was equal to s by g, or sigma max was inversely proportional to the thickness, while it is varying at a higher rate in case of a plate based device, because the material strength also play very crucial role in the plate based devices. Okay. Please note that this equation suggests that a pressure sensor can be designed by exploiting the thin film deflection, and as I have mentioned that it has its own applications. Okay. So, what we have understood from this discussion on plate based devices and membrane based devices is a pressure sensor require two fundamental components for its construction. Okay. The first fundamental requirement of a pressure sensor is a plate or membrane whose area A we already know. Okay. There should also be a detector that respond to the applied force, okay, which actually act as a transducer. Okay. So, you have an area where you are applying a pressure, okay, that area is known to you, be it thin film based or be it membrane based or be it thin plate based, okay, and a detector which can respond to applied force. Okay. It can be, say, piezoresistive devices also. Okay. Now, there is a hint that if these two are the major requirement of a pressure sensor, can we think of a pressure sensor which is built of silicon? we know that most of our electronic devices are built up using silicon microelectronics. Okay. So, what if I can make this pressure sensor from silicon itself, so that its integration with existing electronics will be very easy. Okay. So, people has come up with all silicon based pressure sensor, okay, because both the components, that is the plate or membrane having a known area A and a detector that respond to the applied force, both can be made using silicon. Okay. This is one of the example. You can see that a silicon diaphragm pressure sensor consists of a thin silicon diaphragm which acts as a elastic material, okay, and a piezoresistive gauge resistors which is made of diffusive impurities into this diaphragm. Okay. So, you can see that this is the diaphragm I am talking about, okay, and you have piezo resistances built by the silicon itself, okay, by some implantation in the silicon, or by doping this some area to generate its or to cultivate its piezoresistive property. Okay, and this is how a silicon diaphragm based pressure sensor is constructed. Okay, you have a silicon diaphragm and for the measurement, or which is of course of known area, okay, and the piezo resistor to have the deflection or to convert it into electrical value. Okay. So, due to the superior elastic properties of single crystal silicon, there is no creep, or ideally there is no hysteresis. Of course, there will be hysteresis because it is very difficult to realize single crystal silicon. Okay. So, when subjected to high static pressure. Okay. So, we cultivate basically the elastic properties of silicon in developing this pressure sensor in the form of this diaphragm. Okay. The gauge factor of silicon is, of course, it is a semiconductor. So, it is the gauge factor is several times larger as compared to thin metal conductors. Okay. Please recall the definition of gauge factor. It was a change in a per unit change in the resistance divided by the mechanical strain, or gauge factor is del R by R divided by del L by L. So, del L by L is nothing but the mechanical strain or per unit change in the length, okay, and del R by R is the per unit change in the resistance. So, we have already discussed this in the previous module that gauge factor of semiconductors are several times higher as compared to their metallic counterparts. Okay. So, the gauge factor of silicon is basically several times larger as compared to the metal sheets or metal diaphragm based sensor that you have seen in the previous example. Okay. So, when stress is applied to a semiconductor resistor with initial resistance say R, the piezoresistive effect causes a change in the resistance delta R. Okay, and delta R by R for a piezoresistive material is given as pi L into sigma L plus pi T into sigma T, where pi L and pi T are the piezoresistive coefficient in the longitudinal and transverse directions, while sigma L and sigma T are the stresses in the longitudinal and transversal direction respectively. Okay. So, since I was talking about generating this piezoresistive behavior by doping, okay, so for a p-type diffuse resistors aligned along the say 110 direction, or an n-type silicon square diaphragm like this with a 100 surface orientation, the corresponding coefficients can be approximated as pi L is equal to minus pi T, or pi L is also equal to 1 by 2 into pi 44, where pi 44 is the piezoresistive coefficient defined along the silicon crystallographic axis. If you do not know this pi 44, I will give you a quick recap of this piezoresistive coefficients. Okay. So, piezoresistivity, you know, that can be described using 6 number vector. The change in the resistivity vector delta rho k is related to the stress vector sigma lambda via the piezoresistive tensor pi kappa gamma. Okay. This pi is nothing but a material property that quantifies the sensitivity of the resistivity changes with respect to stress applied. Okay. So, if you talk about the ratio of this resistivity vector delta rho kappa to the scalar resistivity, it is equal to this piezoresistive tensor multiplied with the stress vector sigma. Okay. So, pi into sigma, of course, these notations have their own meaning. This pi into sigma is nothing but the ratio of the change in the resistivity vector to the scalar resistivity. Okay. So, rho naught is the scalar resistivity without stress and kappa. Okay. So, lambda value changes from 1 to 6 to generate a 6 number vector. Okay. Since silicon has a cubic crystal structure, its piezoresistivity tensor contain only 3 independent components, pi 11, pi 12 and pi 44. And from this term, this pi 44, we have got this terminology pi L is equal to minus pi T, that is equal to half of pi 44. Okay. So, since silicon has a cubic crystal structure, its piezoresistivity tensor contains only 3 independent components, pi 11, pi 12 and pi 44. Please remember this. Okay. So, if I write the tensor's equation, this pi value with this k lambda kappa lambda changing, I will have the matrix like pi will equal to pi 11, pi 12, pi 12 and other components 0, pi 12, pi 11, pi 12 and other components 0, pi 12, pi 12, pi 11 and all are 0, then 0 0 0, pi 44 0 0, then 0 0 0 0, pi 44 0 and 0 0 0 0 0 and pi 44. That is how this tensor is written. Okay. So, in a p-type silicon, the piezoresistivity tensor component pi 44 is nearly 2 order of magnitude larger than the other 2 components, and other 2 components are this pi 11 and pi 12, and that is why pi 44 is more relevant in case of p-type silicon. Okay. So, the component pi 44 has significant role in the change in the resistivity when the stress is applied. Okay. Now, change in resistivity is proportional to the applied stress and consequently to the applied pressure. Okay. So, the resistors are placed on the diaphragm so that their longitudinal and transverse piezoresistive coefficient have opposite polarities. Okay. Something like this. Okay. So, the resistors are placed on the diaphragm so that their longitudinal and transverse piezoresistive coefficient have opposite polarity. So, if you are not placing, means you are at least diffusing the impurity in the diaphragm itself. Okay. So, as a result of this, the resistance changes in the opposite direction, and that is why we have seen that pi L is equal to minus pi T. Okay. So, this delta R1 by R1 is equal to minus del R2 by R2, and this is equal to half of pi 44 into sigma 1y minus sigma 1x. Okay, where this R1 and R2 are connected in half bridge, and the excitation, say for example, is E. The output voltage can be written for this kind of devices is equal to 1 by 4 into E into pi 44 into sigma 1y minus sigma 1x, all right, where E was the excitation of the bridge. Okay. Now, as a result of this, the pressure sensitivity and the temperature sensitivity, I am calling it A rho and BT of the AP and BT of the circuit, and it can be determined by simply taking the partial derivative. So, AP, the pressure sensitivity is given as 1 by E, the excitation voltage, into del V out by del P, or this is equal to pi 44 by 4 into del of sigma 1y minus sigma 1x by del P. Okay. Similarly, the temperature sensitivity BT can be given as again by partial derivative, and it is given as 1 by AP into del AP by del T, which is equal to 1 by pi 44 into del by del T of pi 44. Okay. Since this value, this del pi 44 by del T has a negative value, the temperature coefficient of sensitivity for this kind of devices is always negative. Okay. It means that the sensitivity decreases at higher temperature. Okay. This is a little bit about piezoresistive silicon based pressure sensors, which is very practical and very popular in the industry. Okay. Now, if I have to classify pressure sensor based on what kind of pressure it is detecting, they usually can be classified under three different heads, that is gauge pressure, absolute pressure and differential pressure, and exactly in the same form or in same configuration they come into the market. Okay. So, they usually come in three fundamental configuration that allow the measurement of absolute, differential and gauge pressures depending on what kind of pressure you are dealing, and this thing is exactly possible with pneumatic devices as well as with the microelectronics. Since we are discussing this pressure sensor in a course on microsensors and nanosensors, basically based on electrical parameters, okay, we will see that how in the microelectronics this kind of sensors exists. Okay. So, when I talk about absolute pressure sensor, these are devices that can measure pressure with respect to a reference vacuum chamber or say some known pressure. Okay. A barometric pressure sensor can be one of the example. Now, since you are calculating or you are measuring pressure with respect to a vacuum chamber, you should have either a external or internal chambers. Okay. So, chamber can be either external or it can be integrated with the sensing devices. Okay. In silicon, say for example, this structure, this kind of device, okay, this etched cavity in a silicon, which is quite possible with the modern etching technology existing like Bosch process and others. Okay. This kind of cavity is quite possible and this can act as a reference vacuum. Okay. So, this kind of device comes under devices where the chamber or the reference vacuum is integrated with the existing device. Okay. So, this is a very basic layout of a absolute pressure sensor where this everything is etched out of a silicon and this etched cavity is act as a reference vacuum, and other things are like this is the diaphragm, this is the diffuse strain gauge and other metallization for taking contact and other things. Okay. So, similarly the differential pressure sensor very similar to its name. The pressure it measure is some differential pressure. Okay. Of course, the other pressure it should not be the exactly to be a vacuum. Okay. So, it usually help in measuring say pressure between say 2 points. Okay. So, pressure here it say PA and pressure here it is PB. So, this kind of differential pressure sensor will try to measure the difference between these pressures. Okay. So, differential pressure sensor like the pressure drop in a differential flow meter is measured by applying pressure to the opposite side of the diaphragms. Okay. So, this is a basic packaging of this kind of devices are shown. Okay. So, gauge pressure is measured with respect to some reference pressure. Okay. But that reference pressure of course must not be the vacuum that we talked in the absolute pressure sensor. It does not have to be that. Okay. So, basically it is a special case of a differential pressure where the PB for example is the acting as a reference pressure. Okay. So, again here also you are measuring the PA minus PB, but the PB is acting as a reference pressure. Okay. So, the diaphragm and the strain gauge designs are identical in all the three configuration. Okay. So, absolute pressure sensor, be it a gauge pressure sensor or be it a differential pressure sensor, the diaphragm and the strain gauge designed like this is very similar among all. Okay. However, the packaging of these devices are different. Okay. So, for example, in a gauge pressure sensor or a differential pressure sensor, the silicon die, this one, is placed inside a chamber that has two openings on either side of the die. Okay. So, this will ensure the two different pressure or the two different PA and PB can be generated in this kind of devices. Okay. So, I mean, the packaging of these devices are very much complicated. It is not a straightforward method, but we should understand that the construction or the fabrication processes or fabrication steps in all these three devices remain more or less similar, except that there are certain variations. Okay, like you have just seen that the silicon die is placed inside a chamber in case of say gauge pressure or gauge pressure measurement devices, or say differential pressure sensors, and this has two different openings to have two different pressures, PA and PB. If it is a gauge pressure sensor, this PB will act as just a reference sensor, but you of course require a PB. In case of the absolute pressure sensor, you do not require these two, but what you require is a reference vacuum chamber, and depending on what kind of device you have and what size is allowed to you to be utilized. Okay, your chamber can be say internal or external. Okay, we have seen one example where by etching silicon, by back etching silicon, we have generated certain cavity, and it can be used in a seal ambient. It can be used as a reference for vacuum. Okay. So, these are different devices that is possible with the piezoresistive principle, okay, and with of course silicon, and this is the most popular pressure sensor that exists in the market based on this microelectronics techniques. Okay. So, in the previous lecture we have made some base on pressure sensor. In this lecture we have understood some fabrication techniques for this pressure sensor. In the next class, what we will do is we will wrap up this pressure sensor topic with discussion on some more fabrication techniques, as well as we will also try to cover some more pressure sensor transduction techniques like optoelectronic principle, as well as some more devices. Okay. So, we will meet again in the 5th lecture of this module 8. Thank you.